Here's a quick demo of what we just talked about for convexity of functions. I have an obviously convex function here, or concave up. I'm saying here's an interpolated x value between x1 and x0 using my slider for alpha. And so I can slide it between 0 and 1 there. And then here's my interpolated function value, which is using one y value, one function value, and another one, and then doing an interpolation between those. So that's this point. And for every alpha value between 0 and 1, my point on the secant line segment is above the true value of the function at that interpolated x value. Here I've left some room for the slider to go negative just so you can see what happens and why we restrict things to alpha between 0 and 1. And I can just grab a point here and move it. And I mean, maybe it's pretty obvious for a parabola, but we could change this to be e to the negative x. And putting this back down, and you can see any line segment you happen to draw between 2 points on the function will stay on or above the function. So that's our intuition. So according to this definition, would you say that absolute value of x is concave up, or convex? How about that rectified linear, like flat and then 45 degree? Yeah, those are convex. In the multivariate case, so if m and b are decision variables here, and xi and yi are like regression data values, is this convex? Well, you would not want to take derivatives, would you? Because that derivative of absolute value is unpleasant. You could say it's sine of x, sign, but even that has trouble at that at the v point. But if you think about it from region above the function view, then you can convince yourself pretty quickly that that function will still be convex. So that's the sum of absolute residuals in regression. It's nice for that to be convex. Let's talk a little bit more about vocabulary. In calculus, you usually said f double prime has to be strictly positive, not including 0, which would not, which isn't exactly the same as our whole idea of on or above. But in OR, it's pretty common to say that on or above counts as convex. And if you really want some curvature to it, then you can say you want it to be strictly convex, where the secant line segment stays purely above the function. Of course, it's allowed to touch at the two endpoints. Other people want to say convex or concave up, meaning strictly in this point of view. And then if they want to allow the secant line segment to touch the function, then they would say it's non-strictly convex. So it's good to know which of those systems you're using or is being used in an article you're reading. There's other properties called strongly convex and weakly convex that are even more complicated. I often mix up those words, strongly with strictly, but some people are very careful about that, so you need to be careful when you're reading about stuff. There's also some fun definitions called pseudo-convex and quasi-convex, and you can go read about those here if you want to. If a function is convex, it's also pseudo-convex. Anything that's pseudo-convex is strictly quasi-convex, and anything that's strictly quasi-convex is, of course, quasi-convex. And here's some diagrams of them. So they still look fairly nice, but you can tell this part here does not count as exactly convex, and neither does this part. So I'll let you go read about those if you're curious. And then one last thing, can you tell from a contour diagram if a two-dimensional function is convex? What would you expect the contours to look like? Can you draw a contour diagram of a non-convex function that would make you think the function is convex? So take a sec to think about those, and then we'll go illustrate them in Desmos. All right, so here's a function. Do you think this function is convex? That is concave up. Well, we see nothing but positives, so it's probably got a parabola this way for x and a parabola that way for y. Let's draw some contours. I can tell Desmos to graph like, well, let's do this, just to show that we don't have to go by steps of one. So there it's drawing all points in the plane that satisfy this for this list of 10 points or 11. So are those contours convex? Apparently so. Does it seem plausible that if the function is convex, then its contours are convex? That's certainly true. But can we do a function that has convex contours, but the actual function is not convex? Well, let's try changing this to something we know is not convex, or concave up, like square roots. So there, each of these contours is, well, it's hard to say whether it's convex or concave, right? Depending on which way you're thinking of it. So that one is a little non-obvious. Here we know that 0, 0 is giving us a value of 0, and then for larger values, these values are just going up. So anything below this contour is a region with a fairly low objective function value. So that seems to have some concave, non-convex contours. Let's try something else. What if we tried a function that instead of being a bowl upward was a bowl downward? So we could just put x squared here, and x squared, y squared there, just to get back to where we were. And you'd say, okay, that's where we had it, and then if we did that, and put a negative here, then our contours look convex, and they are. But this function is actually concave downward. But you might say, well, we know that here is now a maximum rather than a minimum, so maybe I wouldn't get fooled by this. So think of another way where you could have a minimum here and contours that look kind of like this, but the function would still not be concave up or convex. Well, it's kind of hard to think about it in 2 dimensions at first. Let's try thinking about it in 1 dimension. Let's try this. How about e to the negative x squared? Looks like that. It's our classic bell curve. And if I did 1 minus that, that's an upside down bell curve, which is convex in this region, but then turns concave in that region, right? So now imagine spinning this around the area and then kind of filling in the area above it, or taking contours. The contours are going to be steadily increasing, but let's look at what happens if I make contours that kind of combine these 2 functions. All right, so here I've got a combination of my kind of dip with the bell curve and my function from before, so let's plot that. So I think you'd agree that these contours are all convex, but let's think about what's happening. Here, we know the minimum is 0, and then as you go out from there, it's concave up or it's convex, and we're crossing contours quicker and quicker as we're going here. That function is increasing faster and faster, but then the function starts increasing slower and slower, and the contours, which are evenly spaced, get farther and farther apart. So to tell a function is convex just from its contour diagram, you also have to be thinking about, are the contours getting closer and closer together as I do higher and higher levels, or are they getting farther and farther apart? Even just temporarily, that would be a small non-convexity. All right, so that does it for thinking about contour diagrams, and next we'll go talk about properties of convex functions in the next video.